In this presentation, we will explore statistics and cost estimation and understand how databases estimate query costs for optimization. Let's begin. Let's discuss why query cost estimation truly matters. Executing the same query offers multiple paths. The performance among these paths can vary drastically, ranging from mere seconds to hours. The query optimizer must select the most efficient execution strategy. This decision is heavily influenced by cost estimation. Several elements contribute to the overall cost, including central processing unit processing time, input and output operations such as disk reads and writes, memory usage, and network communication, particularly in distributed databases. Now, let's understand the role of database statistics as the foundation of cost estimation. Key statistics that the database collects are table size, which is the number of rows and pages in each table; column cardinality, representing the count of distinct values within a column; value distribution, detailing how values are spread, such as uniform or skewed; index statistics, covering the height, fan-out, and selectivity of indexes; histograms, which provide a frequency distribution of column values; lastly, correlation, illustrating the relationship between columns in the same table. Let's explore how database statistics are collected. Most databases offer commands to manually update statistics. For instance, you can use the Analyze Table command followed by the table name, such as customers. Alternatively, there's the Update Statistics command, specifying the table like orders. Also, the dbcc show_statistics function along with the table and index name, for example, customers and index name. Modern databases also support automatic statistics collection, which occurs during query optimization, after significant data modifications, during scheduled maintenance, and upon index creation. Histograms provide insights into data distribution. Histograms divide column values into buckets and track the frequency of values in each bucket. They assist the optimizer in estimating selectivity for range predicates and inequality conditions. For example, consider a histogram of customer ages displaying the frequency distribution across various age ranges. On the horizontal axis, we have age ranges like 0 to 20, 21 to 40, 41 to 60, 61 to 80, and 81 to 100. The vertical axis represents the frequency or count of customers within each age range. For instance, the 0 to 20 age range has a count of 60, while the 61 to 80 age range has a count of 350. Histograms like this help estimate how many customers fall within a specific age range when a query involves age-based conditions. Let's delve into selectivity estimation. Selectivity quantifies the proportion of rows that satisfy a predicate. It's calculated as the number of matching rows divided by the total number of rows. A lower selectivity closer to 0 indicates a more selective predicate, yielding fewer rows. Conversely, a higher selectivity closer to 1 suggests the predicate returns more rows. Consider a table containing 1 million rows. If a predicate retrieves 100 rows, the selectivity is 0.0001, which is highly selective. To estimate selectivity for equality conditions like column equals value, the formula is approximately 1 divided by the number of distinct values. For range conditions like column greater than value, histograms are utilized to determine the fraction of values falling within the specified range. For like predicates, fixed selectivity factors are often employed based on the complexity of the pattern. When dealing with multiple predicates, they're combined assuming independence, where the selectivity of A and B is approximately the selectivity of A multiplied by the selectivity of B. Let's explore the cost models for query operations. Several common cost models exist for basic operations. Sequential scan, which involves reading all pages of a table sequentially from the disk. Its cost is calculated as the number of pages multiplied by the cost per read. Index scan utilizes an index to locate matching rows, with the cost being the index height, plus the number of matching rows multiplied by the cost to fetch each row. Nested loop join for each row in the outer table. The inner table is scanned for matches. The cost here is the number of rows in the outer table, plus the number of rows in the outer table multiplied by the cost of scanning the inner table. Hash join builds a hash table on the smaller table and probes with the larger table, costing the number of operations to build the table plus the number of operations to probe the table plus the hashing cost. Let's examine query plan cost calculation with an example query. Consider the following structured query language query. Select customer name, order date from customers, join orders on customers, customer ID equals orders, customer ID where customers, region equals north and orders, total is greater than 1,000. The optimizer evaluates costs for each operation, including filtering customers by region, filtering orders by total amount, joining the filtered results, and projecting the final columns. The overall cost is derived by summing the costs of all operations, factoring in central processing unit usage, input-output operations, and memory consumption. Here are the key takeaways. Statistics are critical. Accurate and current statistics are crucial for generating efficient query plans, as outdated statistics can lead to poor performance. Cost models vary across different database systems, but generally aim to estimate CPU, input-output, and memory usage. Accurate selectivity estimation is fundamental to effective cost estimation, with histograms aiding in handling non-uniform data. Regular updates to statistics, particularly after significant data modifications, are essential for maintaining optimal query performance. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.